Hello, bachon. Welcome. Today, we are going to learn potential energy of a system of charges from Unit 2. Now, I know this topic can sound a little tricky, but trust me, it's a very important idea in physics. I'll make it so simple for you that you will never, ever forget it.
So, let's start with something amazing. You've all seen lightning, right? Ever stop to think where that incredible, massive power actually comes from? It's not magic, I promise. It's all about energy that has been stored up in the clouds, just waiting for the right moment to be released. To really get a grip on what's happening in that lightning strike, we first need to understand what this stored energy really is. In physics, we have a special name for it: potential energy. Now, here's the key idea you have to remember. Whenever you do work against a conservative force, like gravity, or in our case, an electric force, that work does not just disappear. It gets converted and saved up inside the system itself, ready to be used later. And you know what's cool? This idea is everywhere. Think about it. When you lift a heavy rock, you're working against gravity, right? You're storing energy. When you squeeze a spring, you're working against its own force. And again, you are storing energy. It's the same fundamental concept. And believe it or not, this is exactly what's happening with electricity. Imagine you have two positive charges. They naturally want to push each other away. So if you use your energy to force them closer together, it's just like compressing a spring. The work you do gets stored as what we call electrostatic potential energy. Okay, so now let's look at the official NCERT definition. This is very, very important for your exam, so you must know this exact wording. Now, don't let this word infinity scare you. In physics, it's just a simple way of saying a place that is very, very far away. So far that there's basically no electric force. So all this definition is saying is that potential energy is the total amount of work it takes to carry a charge from that faraway place all the way to its final spot in the system. To make this super clear, let's not just talk about it. Let's actually build a system of charges ourselves, step by step. Think of it like we're working on an assembly line. Look here. For our first charge, Q1, we bring it into empty space. There's nothing to push against, so the work done is 0. It's completely free. But now, when we bring in the second charge, Q2, it has to fight against the electric field of Q1, so this one costs some work. And the third charge, Q3, well, that one is even more expensive to bring in because it has to fight against the fields of both Q1 and Q2. See how it builds up? So, what is the total potential energy of the whole system? It's simply the total assembly cost. You just add up the work done in each step. That final sum is the total energy that's now stored in that particular arrangement of charges. It's that simple. Let's take a super simple example. Let's say we bring two protons close to each other. Now, both are positive, so they will repel, right? We have to do positive work to force them together. And so the potential energy, U, will be positive. That plus sign isn't just for decoration, it's telling you a story. It's telling you that energy is stored, and the system is tense, like a compressed spring, ready to fly apart if you let go. Okay, listen up. This is super important. We are going to talk about some silent killers. These are very common mistakes that students make in exams. इसमें बिल्कुल confuse मत होना. Pay very close attention. The number one mistake is thinking that potential energy belongs to just one charge. No, that is absolutely wrong. Remember this. It takes two to tango. You need at least two charges for an interaction to even exist. The energy is stored in that interaction, in the system as a whole, not in any single charge. And here it is, the most common place where students lose marks. Double counting. When you're adding up the energies, you might count the interaction between Q1 and Q2, and then again between Q2 and Q1. To avoid this, I have a very simple trick for you. I call it the handshake rule. This simple rule will save you marks, bachcho. I'm telling you. The energy between charge A and charge B is one interaction. You don't count the energy between B and A separately. It's the same handshake. So just count the pairs once and you will never make this mistake again. Excellent work. So let's do a quick recap of the most important takeaways and see where this idea leads us next in our chapter. So if you remember nothing else from today, remember these 4 points. 1. Potential energy is the assembly work. 2. It belongs to the whole system, not one charge. 3. It's a scalar. No vectors, just add the numbers. And 4. A positive U means you fought against repulsion, and a negative U means you work with attraction. Got it? So, what's the big deal? Why is this so important?
Well, because understanding how we store energy between charges is the fundamental building block for our next big topics, voltage, and the actual devices we build to store and use this energy.
So I'll leave you with a question to think about. It's one thing to know that energy gets stored between charges, but how can we build a device that can do this on command? A device that can store this energy and then release it exactly when we need it? In our next explainer, we will answer that exact question when we study the capacitor. I'll see you then.